So the question asked to propose a mechanism for these transformations. So let's take the top transformation. What kind of reaction is that? And how do you know? Uh, Just in general, what type of reaction is it?
Elimination.
It's an elimination. Why do you say that? You're right. I agree 100%.
Because it's forming with carbon.
I can't really hear you, but did you say something about the double bond being formed?
Forming a pipeline.
Okay, okay, good. That's exactly right. So now we know it's an elimination. The question is it E1 or E2? Let me put a date up here too, right quick. All right, so is it E1 or E2? What do you think? And tell me why.
Doesn't it have inverted stereochemistry?
Well, that's a good that's a good observation, but the fact that the uh, stereo center is kind of gone in the product, and so is the hydroxyl group, right? That's how we know that it's not a substitution. We know it's an elimination, and even if it was an E2 elimination, the stereochemistry it wouldn't factor in. That's only for substitution. That's a great observation, though, right? But what do we know for E2? What is absolutely necessary to do an E2 elimination?
Aprotic solvent.
Aprotic solvents, good. What else? One other thing that's absolutely necessary. You can't do it without it.
The
A
base.
base?
A base, right? So there's no base here. So if there's no base, then we know that this can't be E2, right? This is sulfuric acid is not a base. So we know that it has to be what? E1. Is that right?
Yeah.
All right. So let's go through the mechanism. All right, let me ask this question. Whenever we're doing elimination, what are we looking for? We find our what? Our leaving group, and then what else?
The nucleophile.
Not for elimination. Elimination is that you think about substitution. We find the leaving group, and then we find the alpha positions. Is that right?
Yes.
So here's alpha, and here's alpha. But look at the product. Do we get either one of those products? Right? If we took off this alpha proton, we would get, let me get that. We get a double bond here. If we took off the other alpha proton, we get a double bond here. But do we see either one of those double bonds in the product?
No.
No. So something else had to happen, right? So if we go through the mechanism, we can figure out what happened. All right. So if we go through here, and we know we don't get, let me put this over here. So you get either one of the expected products. All right. So let's go through the mechanism. We know that sulfuric acid is a proton source. And this is an example of one of the reactions we've already seen, acid catalyzed dehydration, right? Because we get this, and let me just put this plus water. All right. So this is my sulfuric acid, like so. And the first step is going to be proton transfer, right? To turn OH into a better leaving group. So proton transfer to get me here. All right, this is still here. All right, now what's the next step in this mechanism? Because it follows the same path as SM1. Is that right?
Yeah.
So what's the next step once I do that proton transfer?
Loss of leaving group.
Loss of leaving group. Good. So that's gonna result in what?
Carbocation intermediate.
A carbo, excellent. Carbocation intermediate. Get that right. That's gonna look like that. Is that right?
Mm.
All right, so now we have this sulfuric acid conjugate base out here. We have water out here. All right, but if we look at that product that we have up top, where would I have to eliminate in order for that product to occur? All right, look at what a double bond is. What proton would I have to pull off in order to get that? Right, let's think about this in reverse terms. How could what would I do with this if the plus charge was right there? Which proton would I pull off? In other words, where are my alpha positions for this proton?
Is there one?
I'm
to
sorry,
the-
this carbocation. Go ahead, Tia. I heard you getting ready to say something.
Is there one to the right?
Right here
Yeah.
and right here, right?
Right.
Okay, good. So which one would you take off to get this double bond right here?
The one on the right.
On the right, this proton right here. There's a hydrogen here. It's not shown because it's in skeletal form, but there's a hydrogen right there. All right. So down here, how could I get to that carbocation? Because that's the carbocation that gets eliminated to give me my product. What could I do? How do you move a carbocation from one atom to another? Right? How could I put that charge on a different atom?
Could
Could I,
you do it by moving one of the alpha protons?
could I do a shift, like some type of rearrangement?
Yeah.
We've done that before, right? We've done it when we were talking about this in part one. We did what's called we can do a hydride shift or a methyl shift
Mhm.
to rearrange that carbocation, and let's see what happens when we do that. So this actually we're going to do a hydride shift. All right, so we're going to take this hydrogen and its electrons and move it to here. So we're actually moving a hydride, H plus a pair of electrons. What that's going to do is give me this carbocation. I'm going to scramble up this. Well, let me not scramble it. I'll just draw it without stereochemistry. Now that's my carbocation. And then that hydride that I moved is now down here, along with the other hydrogen that was already there. All right. Questions about that? right? This is a type of rearrangement. Right, it's a type of rearrangement. If you remember from organic 1, remember we talked about there were 4 types of reactions, right? Substitution, elimination, addition, and rearrangement. So this is one of our 4 types of reactions, where a rearrangement happens when you move electrons across a system, right? You move electrons or atoms and shift them across a system. There are lots of different types of rearrangements, but the basic premise behind it is that you're shifting a pair of electrons and an atom across a system, right? So this type of hydride shift is a 1-2 shift because they're right next door to one another, right? But there are other types of hydride shifts that you can do. All right, so now we're here, and this is the proton that this is now alpha. Make that a different color too. So what happens now? Because that's now we're in a position to eliminate. When we talked about this E1 the other day, how do we show the elimination happening? Anybody remember? Was it the conjugate base that we used, or was it water to do the elimination?
Conjugate base.
We used the conjugate base, right? So we're gonna do the same thing here. We're not gonna do anything new. We're gonna do the same thing here. So we're gonna take the conjugate base of sulfuric acid. Put it here. And just do proton transfer. Same way we did, we would do under any other circumstance. Take a pair of electrons and give it here. Take this pair of electrons and put them here. And that will give us that product. So the expected product we don't see, but the observed product we see. And why do you think that hydride shift happened in past tense? Come on now, Zoom, stop playing with me. Right, look at the, let's compare the carbocations. What type of carbocation is this one? The one, I'm saying this one like you know which one I'm talking about. This one. What type of carbocation is that?
Secondary.
Good, excellent. It's a secondary carbocation. What type is this one up top?
Tertiary.
It's tertiary. Which one is more stable?
The tertiary.
Tertiary. So why do you think the rearrangement happened? This is a really general question too, because rearrangements are not common and they don't just happen. There has to be a reason for that rearrangement to happen.
Is it so that what? Oh, is it to make it more stable?
To form a more stable carbocation. That's exactly right. So when you see a rearrangement happen like that, it usually happens for stability. Right, so rearrangement occurs to generate a more stable intermediate. That's why you don't see the expected products, because you normally, like we said at the beginning, you would expect to see the products from those alpha positions here and here, but you don't. And the reason is because once you get to that secondary carbocation and it's got that branched carbon next to it, that's a perfect opportunity to do a rearrangement to get a more stable carbocation. All right. Any questions about that? So this is a E1 elimination. And the fact that it goes through a carbocation intermediate opens the door for these types of rearrangements to happen, right? If this was concerted, that would not happen. You did this with just a base like potassium hydroxide or potassium terbutoxide or something like that, nothing would have happened. Boom, you just get your two expected products. With a better leaving group, of course, because the hydroxyl group is a poor leaving group. But there's a way to do E2 without having to do proton transfer to make that better. You can add some other substrate and make oxygen a better leaving group. All right, let's do the next. Let's do this problem down here. It's similar. Let's see if we can apply what we just learned up top to this problem right here. You can see right away it's a similar type problem. The alpha positions are here. Well, this is 1. There are no protons here. So that's this, even though it's alpha, you can't eliminate from here. So you don't have any alpha protons there. So really, you literally only have one alpha site, which is the one highlighted in yellow, right? Because that carbon is already quaternary. So nothing you can do there. But it's a similar reaction. What's the first step? I got concentrated sulfuric acid. I'm warming this up in the presence of an alcohol. What's going to happen first? Right. So my expected product, I would expect to have a double bond right here. Let me just draw it. This is my expected product, but it's not seen. Right, I don't see that. What I see is what I have over here. This is the observed product. Look at the star material. Tell me what you think happened. We know it's an elimination because of the pi bond. We know it's E1 because of the acid. What happened? What do you think happened to get to that product? Look at the difference in the two structures and tell me what you think happened.
Do hydride shift or rearrangement?
Some type of rearrangement happened because if you look at the star material, right, you got two methyl groups here, and then the product, let me make them different colors. One of them is in a different location. Is that right?
Mm-hmm.
You see that? How one of those methyl groups has moved. All right, so we need to look at the intermediate to see how we can get to that. And it's really very similar to what happened up top. So what's the first step in this reaction?
Making OH a better leaving group by using proton transfer.
Proton transfer to make OH a better leaving group. Excellent. So I'm coming here, boom, pull that off, give those electrons to the oxygen there. Arrow looks kind of suspect. All right, so I end up with this intermediate, which is going to lose water as a leaving group. All right, and then these are my two methyl groups. I'm gonna keep the same, try to keep the same colors to keep some continuity so we can see what went where. Right, so that's that. That's going to lose water. Is that right?
Yes.
This is nothing new. We've already been through this mechanism. We know once you get OH, once you get the leaving group prepared, if it's not already a good leaving group, the next step, if it's a unimolecular reaction like an E1, is to lose the leaving group. Right, so we go in here. Now I have a plus charge here. I have my two methyl groups here. This one was yellow, red, like that. And let me say this too, so you don't get freaked out about this. But not really freaked out, but confused. All right, there is a hydrogen right here. We just don't see it. Right, that carbon is not charged, and it's not. There are no electrons there. There's no plus or minus there. So even though only 3 of the bonds were shown, the hydrogen is understood, and it's still here. I think you can see what this is setting up to be. I think this is positive, right? And then we see the same scenario now, right? Look at the product. Where's that methyl group that's highlighted in red? Where is that in the product?
At the bottom.
It's at the bottom where the plus charge is. So there has to be some type of rearrangement. Right, so you got a secondary carbocation rearranging to a tertiary carbocation. It's never the other way around, right? You never go from a tertiary to a secondary because you don't want to go from more stable to less stable. But if you have a chance to go from something less stable to something more stable, you do it, right? And so this is a perfect opportunity. You got a secondary carbocation, and notice the setup. You have a secondary carbocation next to a branched carbon, right? That's a perfect setup. It's a dead giveaway that some type of rearrangement is going to happen. So these are kind of like the clues that you look for. So you got a branched carbon there. You got a secondary. Carbocation here. It's a perfect recipe for rearrangement. So what I'm going to do is take this whole methyl group. This is a CH3, by the way. So I'm going to take the whole thing and move it with the electrons. I'm shifting this whole bond to here, right? Which is going to give me an intermediate that looks like this. Well, now this is positive, and then the hydrogen here now becomes my alpha proton. Right, so now I can get to this product just by proton transfer with that conjugate base. That's just going to come in and pluck that proton right off, boom, like that. And then you're going to put that pair of electrons there, and that's how you get your product. Right, but the rearrangement part happens because, again, you have a chance to go from a more stable or less stable carbocation to a more stable carbocation. That's the whole reasoning behind that. So I wanted to show these examples just to, as evidence that the SM1, well, not the SM1, although that could probably undergo some type of rearrangement too under the right circumstances. But the E1, sometimes you'll see these rearrangements happen if the conditions are right, if you have the right type of substrate. And a lot of times, this is not the goal. Like a lot of times when this type of stuff happens, it's more incidental than it is on purpose, right? This is one of those things where you might be wanting to eliminate this alcohol and get a double bond, where you want it. But when you finish the reaction and you take the NMR and you look at the product, what you see is you get this rearranged product instead of what you were looking for. So what that means is that you'll have to find a different way to do it. Right? If you want the double bond to be here, and you got to do it a different way. You can't do it through this method. You have to pick a different method. Normally you just do E2. So you could take that OH and put a tosyl group on it or some other group, and then just eliminate, do an E2 elimination. A lot of times those rearrangements, when they happen, it's irksome because you're looking for one thing, but you get something else. All right, let's go back to any questions about that before we move further. Let's go back to these questions up here. And I'm gonna pull, we already did. Let's do 741. We're gonna pull this one. And then we're gonna do 742 and 743. We'll do it, we won't do them necessarily at the same time. So let's do 741 first. All right, so it asked a question. Which of the following pairs of compounds, for each of the following pairs of compounds, identify which compound will react more rapidly. This is the question in an SN1 reaction, more rapid, right? In other words, which, when we think about SN1 and the rate of an SN1 reaction, what are we concerned with? What's going to increase the rate? Give me two factors that can increase the rate of a SN1.
Can one be the how good the leaving group is?
So the substitution, is that what you're saying?
Mhm.
So what we're looking for in this case is carbocation stability. And we're looking for leaving group ability. Both of those are going to be, this is what we're going to be comparing in this example, right? The more stable the carbocation intermediate, the faster the reaction will be, and the better the leaving group, the faster it'll be. So let's look at A real quick and compare those two substrates and look at where our leaving group is. Which one you think is going to be faster?
The first one.
This one?
Mhm.
Okay, I agree. Why?
Because it's more stable since it's a tertiary.
Tertiary carbon.
Carbocation or something.
Yes, so a tertiary carbon is going to produce a tertiary carbocation, which is good. This is a primary carbon, and remember, SN1 does not happen on primary carbons. It's rare, right? It's very difficult to make that primary carbocation. What about B? Look at where my leaving group is, here and here. Same leaving group, different structure. What do you think?
The second one.
Right, that's faster. Same rationale too. This is tertiary, this is primary. All right, let's do C. What do you think? What are we comparing in C? This is where my leaving group is in both cases. All right, what would the carbocation look like for the one on the left?
Would it just be that that,
Would it look like this?
yeah.
And then for this one, it would look like this, like that. Yeah. Would look like that. Is that right? What can carbocation on the right do that the one on the left can't do?
Resonance.
Resonance. So this is resonance stabilized. Excellent. So if that's a more stable carbocation, the allylic carbocation, then that reaction is going to be faster. Like, so you got the same leaving group, but the structure of your substrate is different. So no resonance there, but you got resonance stabilization here. All right, let's do the last one. D, what are we comparing?
The leaving groups.
Leaving groups are different, aren't they? This is chlorine, this is tosylate. How do we tell the difference in the leaving group? What do we need to know in order? Go ahead.
The pK, the conjugate acid.
Yeah, so you want to compare the pKs. Which one is better, tosylate or chlorine? Or chloride, let me say it that way. Look, don't we have a list of leaving groups?
Mm-hmm.
I think I gave y'all the tosylate. Chlorine has a pKa of well, not chlorine, but the conjugate acid is -7. And then the tosylate is -0.6. Toxic acid, -0.6. Which one of those has a lower pKa? Further away from zero. If it's negative, the further away it is from zero, the lower the number, right?
Yeah, it's chlorine.
So it's this one. It's faster because you have a better leaving group. All right, let's do any questions about that? We're gonna do another example. I'm gonna take it from up here. If you have questions about anything, just stop me. We're gonna do these. We'll just do both of them. Separate them right quick. All right, so let's look at that top one. Let me crop this so I can crop out the bottom. All right, let's take that top reaction. And look at what it's asking. As how would the rate be affected if the concentration of the alkyl halide, which is this, is double? And then it asks, how would the rate be affected if the concentration of sodium cyanide, which is your nucleophile, excuse me, is doubled? All right. What do you think? What do we need to, in order to answer that question, what do we need to know?
If it's SN1 or SN2 or
SN1, excellent. What mechanism is going to go through? That'll answer that, right? So you can look at the substrate. We have a secondary substrate. All right, that's secondary. We got an aprotic solvent. And we have inversion. What does that tell me? All those things together tell me what?
SN2.
That is SN2. So if it's SN2, what is the rate law?
K times the substrate and the nucleus, and then times the nucleophile.
Right. All right. So about double the concentration of the substrate, which is the alkyl halide. So this is 2. And this is 1. What happens to the rate if that's a product?
Would increase by 2.
It should double, right? So you should see right, you should double the rate. This is a second order reaction. First order in each one is first order in nucleophile and substrate. So second order overall. Anything you do to either one of those terms is going to change the rate, alter the rate. So if you double one and leave one constant, it's going to double the rate. What about B? How would the rate be affected if the concentration of sodium cyanide is double?
Would it double 2?
It's going to double also. So this is 2. All right, so the rate should double here as well. Right. If I have, if this is, what if I double them both?
Yeah, quadruple.
4x, right? 4 times increase. If I triple them both, it'd be a 9 times increase, so on and so forth. All right. So we know that it's SN2, right? We know that based on all the clues that are given. You got inversion of serial chemistry, a protic solvent, a secondary substrate, a good leaving group, and a good nucleophile as well. All right. Let's do the next one. Let's do 743. What do we need to know about this in order to answer these questions?
Whether it's the SN1 or SN2.
You know the mechanism. Can't answer the questions about the rate unless you know what the mechanism is. What do you think? Is it SN2 or SN1?
SN1.
It's got to be SN1 for one reason that we can look at everything else, but this is a tertiary substrate. Right, my leaving group is on a tertiary carbon. Tertiary carbons do not do SN2 substitution. Right? So if we know it is SN1, what's the rate law?
K times the substrate.
And that's it, right? That's what the 1 means in SN1, that is unimolecular. So what happens if I double the concentration of the alcohol? That's the substrate.
It increased by 2.
Right. The rate should double. All right. And then the other part asks, what about if the concentration of HBr, which is the source of your bromine nucleophile, if that's double, what happens to the rate?
It doesn't change.
No change. Good. All right. Unfortunately, we got to stop here, but we'll pick this up Wednesday. We're going to finish this handout on Wednesday, so make sure you have it with you. And there may be some group work depending on how far we get, but we'll figure that out on Wednesday. But for now, we're going to stop here, and then there's going to be one problem out of this that I'm going to assign as on your own, but the rest of them we'll selectively work through the other ones. All right. So make sure you check that ranking nucleophiles video that I sent you. make sure you look at that because that's one of the problems we're gonna be working through on Wednesday. All right, so I'm gonna stop sharing, stop recording, and you are free to